So, hello everyone. I'm Lorenzo Maggi, now at Nvidia, Paris. So, welcome everyone for this probably shorter than usual, so I probably will not take the whole hour to talk about some very classic topics in optimization, but hopefully under uh, interesting, let's say, perspective. So usually these topics are not taught this way, unfortunately, I would say, because I would have found it easier to understand in the first place. So it's something that I was asked to do quite recently, so I didn't really have time to to make new material. But it turns out that I wrote a blog post on my blog that I do for, let's say, for fun. Although fun is not probably the right word because it's a lot of work. So I'm going through, let's do an experiment and I'll go through the blog post itself. So probably you will be enticed to read, which is not great. So some visual could be better, but I have some figures that apparently were well received on LinkedIn. I received a lot of feedback on how good my visuals were. To be honest, I don't think they are so good, but at least they convey some message. So let's delve into the problem here. So we consider constraint optimization problems. Very simple kind of them. So we want to maximize a function, let's say any function, such that these constraints are respected. And by the way, do you see the cursor of my mouse?
Yes, we do.
Yes, okay, great. So the constraints are in the linear form, although these famous KKT conditions apply to any form, but I think that it's much better to learn this way and then to generalize to any kind of constraint. So let's say that we have this polytope that this point has to lie inside. And then we want to find the x star that maximizes a certain function. Okay, so let's start by conveniently rewriting this constraint in matricial form in the following form. So it takes, let's say, more time to write, but you will see that it will simplify.
Lorenzo, can you
Yes?
make it bigger? I'm old. I'm becoming old, so.
I know, I am as well. Like that, is it okay?
Better, yes.
That's better? Okay, let's try like this. And by the way, hi. So we decompose these constraints in a row-wise manner. Okay, so we say that the ith row of this matrix A, scalar product X must be smaller or equal than the ith element of B, and the same thing for the equality constraint. You will see that we will start with the inequality constraint first and then add the equality on top, because really equality is like twice an inequality. So you will see that you will start really simple. So in a nutshell, what we will discuss are these KKT optimality conditions. What are they? So basically, these are conditions that any optimal or at least local optimum point has to fulfill. And in simple words, they say that very intuitively, if you're in an optimal point X star, and you move out of this X star, the function f must not increase. Okay. So because otherwise, if f increased, then X star would not be optimal. There will be some other x that is better than x star. Okay, so but we immediately realize that this definition is really not, actionable. It's not really not what we want, because first of all, what does it mean a feasible neighborhood? So we said that an optimal x star is such that within the feasible region, the f must not increase. But what does it mean to stay in the feasible region around x star? So also, how do we know from just looking at the f, the function f, whether it does increase or not within the neighborhood? And here you may already realize that it has something to do with the gradient, okay? And then we want to also to restate the optimality condition such that we can do something with it. So it's not only an abstract definition, but also we want to use it to actually compute sometimes the optimal point, okay? So we will go, let's say, in order. Let's start, let's say, simple with this non-increasing property. So what does it mean that a function is not increasing? It means that its gradient is smaller than 0. Not really. So this is true in the 1D. The derivative has to be negative. In more than one dimension, we also have to define the direction towards we are looking the function, because in 1D there is just one direction, right? Then you can go left or right, but then there's just one direction. In a n dimensional space, you also have to define the direction v over which you want to assess whether the function is increasing. And so in this case, you must, in order to compute the directional derivative over v, you do the scalar product of the gradient and the direction, and you say that it must be non-positive. And if this is the case for all possible directions from x star, then it is true that x star is at least a local optimum, okay? But then immediately a question arises, okay, what is this fx star? So this is fx star is the set of feasible directions. What is a feasible direction? So you start from x star, you walk away from x star along a direction, and the feasible direction is such that as you walk along it, you stay in the feasibility region at least a tiny bit. Probably not all the time, because at some point you will go outside, but at least you stay in the feasibility region for a tiny bit. Okay. So so the optimality condition can be restated as the gradient at the optimal point, scalar any feasible direction is non-positive. Then how to define this set of feasible directions? So you will see, we will build up to the known KKT conditions really from first principles, okay? So this is our first, let's say, definition of KKT condition. Okay, what can we already say? It's very primitive, but we can already say something that is very well known, but that it stems directly from this. If x star is in the interior, is inside, okay, the feasibility region, then it must hold that the gradient is equal to 0. Okay, and this stems directly from this, because if it were not equal to 0, then there would always be a direction over which you can stay in the feasibility region that is aligned with the gradient. And in that case, the scalar product will be positive. So the only way for it to hold if X star is inside the feasibility region is to just straight away, the first place, let the gradient is equal to 0. And this is the classic unconstrained optimality condition, where basically we just have something like we want to maximize function f where x can be anything. In that case, the gradient must be 0. Okay. Okay, so next step is defining this set of feasible directions. Okay, so let's take it again. So we are at X star. We walk away from X star in a certain direction. We say that this is a feasible direction if you stay at least a little bit in the feasible region. Okay, if you go outside the feasibility regions right away, then this is not feasible direction. Okay, and this is the first illustration that helps us understand a little bit more. So let's say that your feasible region is something like that. This triangle. So you're here, and your feasible directions are all these directions. Okay, because if you follow this direction, you stay in F. This is not clearly a feasible direction. Okay. So how to define them? So it turns out that if the feasibility region is convex, and this is our case because it's polytope, then you can define this set of feasible directions as basically all the misplacement V that bring you from your starting point to any point in the feasible set. So formally is this thing, okay? So why it is not the case for a non-convex feasibility region? Because it may happen that you take a point in the feasible direction, you misplace your initial point to that point, but this is not feasible direction because you have actually gone outside the visible region and then you went inside back in. Okay, and this basically stems directly from the definition of convex set. Convex set is a set such that if you take 2 points, any point in between these 2 points is in the feasible set. Okay, so it turns out that this feasibility, so this feasible directions are defined quite easily like that. So it's the set of misplacement such that they bring you to any other point in the feasible region. So basically, we can rewrite the optimality condition that was here, as something, let's say, more not readable, but more actionable. Because before we didn't know what this feasible direction means. Actually, this new definition is only a function of something that we know, the feasibility region. Okay, so and it says that if X star is optimal, then it must be, let's say, anti-aligned. So its scalar product with any vector of this kind must be non-negative. Okay. We still have another problem. So we don't really like F, because F can be arbitrarily, let's say, complicated. So 2D, okay, you can have a look visually of what it looks like, and you can basically understand. But in multiple dimensions, this is not really what we want. We would want basically an expression that is just a function of these A's, of these B's, probably not, but of these A's and of these C's, and of this clearly F, but the F is already included in the grid. Okay, so we want something that includes this too. We don't want F. F could be something very complicated. So let's do yet another step towards the final definition. So we are here. We want to get rid of F. So in order to do that, we start realizing that this has a name. In mathematics, this means that the gradient of F at x star belongs to the normal cone of F at x star. So for those who don't know what it is, basically normal cone. So there are two actors here. There's a set F, our feasibility set, and a point x star. So the normal cone of F at x star is the set of all vectors such that these vectors are anti-aligned with any feasible direction from x star. So you take x star, you take x prime, you go away from x star while still staying in the feasible direction. If the scalar product between x prime and any of this feasible direction is non-positive, then your x prime is in the normal cone. You may wonder how on earth this actually simplifies our life. For the moment, it actually complexified our life because we have yet one more definition. Thing is, we can define the normal cone, let's say easily, as a function of A's and C's, okay? But for the moment, let's just even discard equality constraints. So we will only have A's, we will not have C's, but you will see, you will add them later. But it's really, the only important thing is the inequality. Again, the equality can be seen as two inequalities. So our next goal is to define this normal cone, okay? So we have rewritten the optimality condition as gradient belongs to normal cone. But what the hell is this normal cone? Okay, let's start simple, and let's start with the case where the x star, our optimal, lies in the interior of the feasibility set. This is actually something that we've already seen, and we have seen that the gradient has to be equal to 0. Does it comply with this new definition? Well, yes, because if you're here, your normal cone is 0. Why? Imagine that your normal cone were not 0, and we're, I don't know, this vector here. Well, it's always possible to find a feasible direction that is aligned with this vector, so its scalar product is positive. So whenever you try to enlarge your normal cone in some direction, well, you cannot, because there's always something that is aligned with it. So normal cone is something that such that all the feasible directions are anti-aligned with it, okay? So it's not possible. So basically the normal cone is actually 0, so it complies with our initial definition. If the x star is inside, so our optimal or local optima is inside the feasibility region, then the normal cone must be 0. So this means that the gradient is 0. And this is classic stuff. Unconstrained problem is as if it were unconstrained, because no constraint is tied. So it just means that the normal cone is 0 and the gradient is 0. Good.
Lorenzo,
so, yes?
Just for the notation you use, when you say that the normal cone is 0, you mean that it only contains the null vector?
Exactly. Yeah, exactly.
The notation is a bit ambiguous, sorry, for me.
Yeah.
But it's okay.
Yeah.
It's okay.
Probably. I should put. Okay. Yeah.
You
Yeah.
should have
You're
put a
right.
bracket.
I can change it.
No, it's okay. It's okay.
It got updated quite a few times, this blog. So I received a lot of feedback. So thanks. Always welcome. So now let's take the next step. Let's say that the X star is not in the interior, but only one constraint is tied. So all the others are not tied. Okay. This basically this edge defines a constraint, right? This edge defines another constraint, and this edge is a third constraint. So this means that only this constraint, A1 scalar X, smaller or equal than B1, is tied. So it means that A1 scalar X star is exactly equal to B1. So basically, X star is on this edge. Okay. So A1 is, as you all know, perpendicular to this edge, and on the other side, right? Because we want X scalar A to be smaller than B. So A has to point outside the visibility region. Okay. So imagine that X star is here. What is the normal cone at X star? Well, this normal cone is just something that is aligned with A1. Why? Well, already, is it true that anything that is aligned with A1 and in the same direction as A1, this is important, is in the normal cone? Well, yes, because if you take any visible direction, it is anti-aligned with A1, right? Because it lies on the other side of the hyperplane. So, yes, at worst, it's equal to 0 here, okay? But otherwise, it's strictly negative. Can we find any other direction? Well, no, because if, for example, visually, of course, this is all visual. If we try with this direction here, well, it suffices to take this visible direction, which is aligned, okay, which has an angle which is less than 90 degrees. So no. This is not possible. Same thing on the other hand, on the other side, okay? So normal cone is just this line here, this segment, this half line. So it means that, for X star to be optimal, the gradient has to be aligned with A1. That's it. Two constraints are tied, and then I promise I will not do 3, I will generalize straight away. But this is, I think, the most important, let's say, concept, probably. So two constraints are tied. It means that X star, and I hope that you can see it well, because it took me some time to do this one. So two constraints are tied. So basically, X star is here. So there's this constraint and this constraint which are tied, and this is not tied. Okay, so we basically don't care about it. We only care about this too. What does the normal cone look like? So let's start with the negative example. Can this vector be inside the normal cone? Well, no, because basically any point here, any visible direction here is aligned with this vector, right? So no. And actually, the figure says that if take a vector, take the hyperplane on associated with this vector, and that points the other direction. So in order for this vector to be in the normal cone, it means that the visible region has to be contained in this hyperplane, and this is clearly not the case. Okay, it is contained in the upper plane if the vector is in between, let's say, A1 and A2. In fact, if the vector is here and you draw the hyperplane associated with that. F, so feasibility region lies completely inside of it. So if you imagine to rotate this vector up to here, same thing, it's still inside. As soon as you get outside this magic region between A1 and 2, then you're not good because the F is not contained in it. Okay, so basically visually we have gotten to a very let's say profound concept that says that basically the normal cone at the point that is at the intersection of several constraints here too is actually the cone generated by the vectors A that define these constraints. And this only holds for the constraints that are tight, right? Because for this constraint is as if it were not even present. If this constraint were not there, so we would have something that goes to infinity and we would not care. So that does not get into the picture when defining the normal cone. Okay, so basically, mathematically, this can be seen as any linear combination of A1 and 2 where the coefficients are positive. And this is exactly the cone spanned by A1 and 2. So in this case, we have seen that the normal cone in here is the cone spanned by A1 and 2. So it means that if we go back to our initial goal, it means that the gradient has to be inside here, inside here. And I think that I have one. Okay, let's get to this figure already. So it means that
Lorenzo.
Yes.
Hello, this is Marco. Sorry, just to be sure to understand, what you call cone is actually a polytope defined by those normal vectors.
Yeah,
you call it cone. It is a cone, but it's a polytope actually.
It is a polytope. Yeah, it is a polytope.
Just to be sure. Okay, thank you.
Yeah. It is a polytope, and it's also a cone defined. By this vector, spanned by this vector. Exactly. So basically, putting all things together, it means that the gradient of this function. Okay, you see that before we didn't have any function; we just have the feasibility region. Now we also introduced the function that, and these are basically the contours of the function. The gradient, which is perpendicular to the contour of the function, has to lie inside this normal cone, which is the cone defined by blah blah blah. And if this is the case, well, no, it's not actually sufficient yet. But so it means that any optimal condition must be optimal point must satisfy this. Okay. Let's take a little step backwards now. So if multiple, so we've gotten here so far, right, with two constraints which are tight. If multiple constraints are tight, basically it's the same story. But the new thing that we have introduced here is this condition, which is called complementary slackness. What does it say? So the first one is the classic one. So this is exactly the cone defined by the A's, okay? But here we sum across all constraints. But then we also said that we don't care for the constraints which are not tight. And this is exactly what it says. It says that when the constraint is not tight, so this is actually not zero, then lambda has to be zero for this to hold. So it means that this sum is not over all constraints, but there is only across all the constraints for which the constraint is not tight. Okay, so it's not actually a sum over all i's, but it's sum over i's such that the constraint is not tight. Okay, so here it would be a sum over 1 and 2, not 3. Okay, but this is, let's say, a fancy way to say the same thing. So to introduce this one more constraint that I really never liked, in the sense that well, one has really to think what it means. It's not just any constraint. Okay. Okay, we're almost there. Almost there. Why almost? Because we still have to bring back equality constraints. We said, okay, let's stash them away for the moment, but then at some point we have to deal with them. Okay. So here the feasibility region is actually now AX smaller or equal than B, and CX is equal to D. But really, as I already repeated 3 times, if we rewrite CX equal to D as a 2 set of constraints, then it's basically the same thing. And which set of constraints? Well, basically, we like inequalities in one sense, so smaller and equal. So we rewrite the equality as CX smaller than D and minus CX smaller than minus D. Okay, this is just to preserve the inequality in one sense. And if you do that, well, basically you end up, so basically if you do that and you treat them as 2 separate inequalities, you end up with something a little bit messier. So you have this is that stays the same, but then you have to count basically twice the same inequality, and you have the multipliers that now we call mu instead of lambda to distinguish them. But
Lorenzo?
at this moment, yes, please.
Sorry to interrupt you, but just before your 2 inequalities are actually the same, I guess that there is an extra minus. There is an extra minus sign. Because if you want CL dot X equal to DL, so the first inequality is correct. The second one should have only a single minus sign. No.
No, because if you see the difference, so if you multiply by -1 left and right, you end up with a CX greater or equal than D. So basically, it says CX is at the same time smaller or equal and greater or equal. So it must be equal. Okay. So basically, it's like that. So so we said we are at this point where we have a slightly more complicated expression for this normal cone, but then we realized that a difference between 2 positive numbers can be either positive or negative. So there is no reason to have this lambda 1, lambda 2. We just call it, sorry, mu prime and mu 2. We just call it mu, and this mu can be either positive or negative. So basically it has to be real. Okay, so we've gotten finally to the let's say most well-known expression for the KKT conditions. Let's say, okay, if X star is optimal, then there exist, doesn't say which ones, be careful, but there exist some lambda and some mu, such that the lambda are positive and mu can be anything, such that the gradient can be written as a linear combination of A's and C's and complementary slackness. The lambdas only have to can only be positive if the constraint is not time. Okay, and just note that this complementary slackness basically we don't write it here because the constraints are always tied by definition. Okay, so this is already by definition always true for equality constraints. Okay, so this is arguably the classic way to write KKT conditions, but usually people get to that in a very different way by defining the Lagrangian function, by defining saddle points, and so on, which personal taste I've never really liked and never really fully understood, at least visually. I think that this is probably a better way to at least to learn it because it has some visual interpretation at least, okay? And then you can write blogs about it. So I think that I will not go through the formal proof I was planning to, but given the time, probably it's better to go to the example. But this is basically a formal proof of of the fact that the normal cone is exactly equal to the cone spanned by this A1 and 2, and the proof holds for any number of A's. Okay, for those who are interested, I think it's a nice one. I found it somewhere. Then I tweaked a few things to make it more understandable, hopefully. But okay, you can have a look if interested. And last thing is, can really all this machinery actually help us do something? Because for the moment we only said, well, there exists some lambda and mu such that, but can we actually compute them and in the end compute the optimal solution? Sometimes it is the case, sometimes it's not. But at least, most of the time, it gives us really some intuition of what the solution should look like. So let's look at this optimization problem that for those who work in telecom, you may have already recognized. So one can interpret this as the rate, the classic Shannon formula. This can be interpreted, let's say, as the transmission power times the channel gain. This can be interpreted as the noise power. And this can be interpreted as constraint on the powers. And instead of one, you can put whatever you want, okay? So basically, in some sense, we're trying to maximize the sum of the rays across users by tweaking the powers. But at this point, we don't really care about the analogy. We just care about writing the KKT condition and see whether we can do something with them. So let's start by computing the gradient of the function. So here, f is this log of 1 plus x over n, okay? And believe me, just 2 lines, this gradient is equal to 1 over n plus xi, right? So it's 1 over this multiplied by 1 over ni. So this is the result. So the A1's vector. So first of all, how many there are? So there are m A1's, right? And each inequality is really simple. It's just one component. And also it's in the other sense. So it should be minus xi smaller or equal than 0 if we want to comply with our formal definition. So ai is 0 except for the ith component being 1. And then let's see how many equality we have. Just one. So there's just C1, which is a vector of 1's. Okay. So according to the KKT condition, if x star is optimal, then there exists some positive lambdas and some real mu, such that the gradient can be seen as the sum of mu a's and lambda a's plus mu c. And since we have this very, let's say, sparse definition, it turns out that if we write this vector relationship on a component-wise manner, we have this relationship, right? Because there's only the ith component that survives at this row. And this is the classic complementary slackness constraint, So rewriting this as a function of x star equal to something, we have this expression. However, from the complementary slackness, we know that if x star is greater than 0, then lambda has to be 0, right? So basically, here we can basically kill lambda I, because we are only interested in the xi's that do something. Moreover, the xi must be positive. Then basically we kill lambda, and we basically take the positive part of what's left. So we are left with this x equal to this expression. But it's not yet the optimal. So this is the problem here. So this is the optimal depending on the value of this multiplier. So it's not yet the optimal. So we cannot really do much about it. So there's this mu that we don't know. However, and this is where the creativity, let's say, comes into play. KKT do not provide you with a method that you can just apply, but they provide you with some intuitions. Then you have to do something on top. That something on top is, well, how to find the mu such that this works. And we know that these xi's have to be there's some that has to be equal to 1. So we want to find the mu such that this holds. Okay, so we have an expression that depends on mu, and then in order to find the good mu, we say, okay, which is the good mu such that the constraint holds. Well, this just boils down to the search of the root of a function. Where this function is this thing that has to be, well, if you want this thing minus 1, which has to be equal to 0. The good thing is that we know that this function is decreasing with mu, right? If mu increases, this decreases. So the whole function, the whole sum decreases. So we can just use bisection search, for example. So we have a function. We know we don't know mu, but we want its root. Easy. Okay. So basically, we have, let's say, a procedure to compute the optimal x starting from the KKT condition. And by the way, this is called water filling, and it has a very nice visual interpretation that I didn't find the time to put in figures. Probably should. Where water filling means that basically it's as if you had, let's say, some vessels that are communicating, okay? And you're pouring water in these vessels. And each vessel has a depth of this. And this is basically this, okay? So you're pouring water until the total amount of poured water equals 1. Why 1? Because actually each vessel, you can interpret each vessel as the xi. The optimal value of xi is a function of mu. So that is the root search basically coincides with pouring water until the amount of poured water equals 1. Okay, so this is why it's called water filling. That's a very nice visual interpretation. So just to conclude, it is not easy mathematically, but I think it's easy intuitively to extend all what we've said to nonlinear constraint. Well, when we have nonlinear constraint of the kind, not let's say a scalar x, but any function of x smaller or equal than bi's, such that, let's say, and same thing for the equality. Well, what the intuition says is that in the infinitesimal small world, this is actually behaving as a linear function. So basically, we can perform the first Taylor expansion of this function and get back to the initial expression, and everything holds the same. And and basically the intuition holds because indeed, if we do that, we just replace AI with the gradient of the function and CI with the gradient of the second function, and everything works the same. So instead of having this expression, you will have, instead of A, you will have the gradient of the G's, and instead of C, the gradient of the H. And this is, let's say, the most general KKT condition that you find on any material, say Wikipedia even. This is all I wanted to say, except for the proof, but okay. I think it's okay. So if you have any question or so everything is online on let's say my blog, where I try to post things on the average of once a month, but it's not really binding. I mean, it's not a job. It's something that I do in the evenings and sometimes in the weekends when my wife and the kids allow me to. So, but it's fun. So thanks a lot.
Thank you, Lorenzo. Maybe put the address in evidence so people can bookmark you. It's a very good read, a very dense read, and I like it very much. So thank you for putting up with all this work.
Thanks to you for the opportunity.
I don't know if there are questions. Doesn't seem to.
Just a comment on my side. So I thank you, Lorenzo. I really appreciate also this presentation. I use the Lagrangian method for to apply the principle of entropy maximization. It is also used in that case to find the probability distribution that fits a prior knowledge. And for me, it was so I know how to apply this method, but it was not so clear. And I really like you this kind of approach that is quite intuitive and geometrically representable also. So I really like this kind of presentation.
I agree. If you start from the Lagrangian function, then a lot of doubts start popping in. If you
I had the receipt, so I applied the receipt, and then
exactly.
I found the result. But no, I had a question, but your chapter 7 here answer to this to my question. I was planning to ask you if it was if we could apply this to nonlinear constraints, in fact.
Yeah, absolutely.
But you still need to have something.
Becomes nasty.
Yeah. But you need to have something that is convex still.
Yeah, it is convex. Exactly.
But then you can apply
normal cone, exactly.
with
Normal cone of the convex set.
You can apply with spherical, for example, constraints or things like that.
Yeah, as long as it's convex, exactly. Yeah. Exactly. But the method becomes much more nasty, and to be honest,
it's a matter of yes, you use the gradient. In fact, I think I remember. If I remember, I have some solving. I need to solve some equation using the gradients of the constraints.
Yeah, exactly. Okay, thank you. Okay, there are no other questions. Thank you again.
So thanks a lot, Lorenzo. It was very good to have you back. We hope to see you soon again.
Yeah, hopefully in person as well.
Yeah, that would be nice. This week the weather was not with us, but yeah, for the next one, we will have pizza as well after the talk. So
then I'll be there.
For you, Francesca, yes, I just check on the invitation, the link to the document of Lorenzo was given.
Perfect. I don't have the.
So it should be also I think in the links website.
Perfect. I lost the invitation. I don't have it in my calendar anymore. So yeah.
It must be on the website of the links then.
Perfect. So thanks a lot, and see you soon.
Thanks. Bye, everyone.
Bye bye.
Thank you, Lorenzo. Bye bye.
Bye bye.
Bye. Thanks.